Hello, everyone. I am Marina Jurica, and welcome to NASA's Jet Propulsion Laboratory. Today is a very special day as we celebrate the legacy of the Spitzer Space Telescope. Spitzer is a telescope that has observed things in our own solar system and far beyond. After over 16 years of incredible discoveries which impacted how we see the universe, the world will continue to benefit from its monumental impact for many years to come. To grasp the wonders of the cosmos and understand their variety and beauty, NASA launched its 4 great observatories: Hubble, Chandra, Compton, and Spitzer, who apart and together gave us an extensive look into places we only dreamed of. Spitzer observes in the infrared wavelength, giving it no shortage of things to look at, while a whole new universe was unveiled. Throughout the program, we are inviting everyone to ask questions of our panelists. If you are a member of the media on our phone lines, just make sure that you press *1. And if you are a member of social media, make sure you use the hashtag #AskNASA. Joining me now from NASA headquarters is the head of astrophysics, Paul Hertz. Welcome, Paul, and thank you so much for helping us celebrate the legacy of this amazing telescope.
Well, Marina, it's my pleasure to be here today.
Paul, tell us why we are celebrating here today and what Spitzer has meant to the world.
Well, at NASA, we're interested in answering the big questions in astrophysics. How did the universe begin and evolve? How did the familiar night sky full of galaxies, stars, and planets come to be? Where did the elements of life and life itself come from? And are we alone? Now, these are hard questions, so we need to use all the evidence that the universe provides us to help us answer them. And that means observing the universe in every kind of light there is. In every kind of light there is, not just the light that gets through the Earth's atmosphere and can be perceived by our eyes. And since NASA goes into space, we can put space telescopes above the blurring and obscuring of the Earth's atmosphere. Back in the 1970s, NASA began a program of great observatories. The first of the great observatories was the Hubble Space Telescope, which observes the universe in the optical and ultraviolet. Hubble will be celebrating its 30th anniversary later this year. The next great observatory was the Compton Gamma Ray Observatory. Compton observed the universe in gamma rays, and it completed its science mission in the year 2000. The Chandra X-ray Observatory is NASA's 3rd great observatory, observing the universe in X-rays. Chandra celebrated its 20th anniversary in orbit last year. NASA's 4th great observatory is the Spitzer Space Telescope, our infrared great observatory. The Spitzer Space Telescope will be completing its 16-year mission next week, and we're here to celebrate and discuss the legacy that Spitzer has left for us, how it has changed our views of our solar system, of our galaxy, and of the universe itself.
Thank you so much, Paul, and what a legacy it does leave behind. We will bring Paul back a little later in the program to talk about how Spitzer will be a pathfinder for both scientists and future missions. But for now, let's take a look at the last 16 years.
3, 2, 1. We have ignition.
Rocket launches. It's thrusting out flames, and you're watching, and you have all those emotions, and the rocket goes along on this journey, and it deploys Spitzer.
The Spitzer Space Telescope is a member of NASA's family of great observatories. Spitzer is the infrared member of this family.
Spitzer has unveiled the infrared universe. It has enabled humans to see what our eyes could not see.
We see a whole new side to the universe that's hidden from us normally.
You can peer inside of clouds of dust to see the baby stars called protostars being born.
It let us see into more distant galaxies and see how the patterns of dust tell us about the motions of gas and the dynamics of gravity that operate in these objects. all of a sudden we could create these vast panoramas at incredibly sharp resolutions that we'd never been able to do before. And as a result, everything that was familiar in the sky, every nebula that we're used to seeing in visible light images from the ground, things from Hubble, they became completely different when seen through the infrared eyes of Spitzer. It was this combination of a scientific insight that itself was just stunningly beautiful at the same time.
The biggest surprise in terms of what was revealed with Spitzer is its ability to characterize exoplanets, so planets around other stars.
Most notably, we identified a system called Trappist One, which has 7 Earth-sized planets sort of snuggling up to what's a very cool star. And of those planets, 3 of them at least are in the habitable zone.
When Spitzer launched, exoplanet science was absolutely not part of the science portfolio we were offering for Spitzer because it wasn't considered to be sensitive enough to do that kind of observations. But while in flight, astronomers became clever about how they could use it, engineers became very clever about how we could repurpose Spitzer, and exoplanet science has actually become one of the core science projects of Spitzer since then.
The Google Doodle that day, which was Trappist One, is what kind of finished me off on a glorious day. When your adult children point out that, you know, my mom works on that telescope, you know, that's very rewarding.
Spitzer Space Telescope is a technological marvel.
I never had any conception that we'd be going for 16 years.
The little machine that could go beyond its primary design.
The longevity of the mission is a direct result of the engineers and scientists and people that have supported the mission.
In a place that dares mighty things, you can do it together. And so when you have that kind of union, I think what happens is magic.
I'm hoping Spitzer will be remembered as a really amazing scientific gift, and that it allowed us to kind of transform our understanding of some very important aspects of astronomy, and I think Spitzer's been integral to all that.
We have a huge archive that is waiting to be mined, and its revelations already have been tremendous and revolutionary, that only time will tell what is Spitzer's greatest legacy.
Let me now introduce you to Joseph Hunt, Spitzer Space Telescope Project Manager, and Suzanne Dodd, a former project manager for the mission. Welcome and thank you for joining us here today.
Thank you, Maureen.
So, Suzanne, let me ask you about Spitzer's 4 great observatories and what part it plays in those 4 great observatories and what sets Spitzer apart.
Certainly. So as Paul mentioned, Spitzer is part of NASA's Great Observatory Program, the 4 great observatories, and Spitzer measures in infrared light. So infrared light is senses heat of coming off of objects. It's similar to night vision goggles, if you're familiar with how those work. And the importance of infrared light, again, is it senses heat, so it can see through dusty clouds, and it can see through the dust that is in an image, say, from Hubble. Spitzer can see through that to see star-forming regions, to see galaxies forming and merging, and just a whole cornucopia of objects in space that are not visible to our eyes in the optical, but are visible in infrared. And one of the unique things about Spitzer that makes this all possible is its orbit. So Spitzer was launched in 2003, and it's in a very unique Earth trailing orbit. So what that means is that Spitzer is launched into the same orbit around the sun that our Earth is, but it trails away from the Earth slowly. So it's circling the Earth, it's circling the sun, falling behind the Earth. And I have this little model here, and just to show you this the Earth would be talking to and from the high gain antenna on the bottom, and then the solar panel is always pointing at the sun. So it's coming around, it's leaving the Earth, but we get our power from the solar panel, and then we communicate with this high gain antenna on the bottom. So it's a very unique orbit, and it's unique because it's drifting from the Earth and the Moon, so it's not getting the infrared radiation that the Earth and the Moon system create. And it's also up above our atmosphere. You would have to have a telescope on the ground 10 times as big as Spitzer to get the same quality data that Spitzer gets from being above our atmosphere here at Earth.
And that's what makes it so unique and so special, for sure. And welcome, Joseph. How's the team feeling in anticipation of the big day next Thursday?
Well, working with the Spitzer team in general, they're always excited about any of the activities that they have to pull together for the next great science observation, and they're planning for the end of mission. I think this team stays focused all the time, even though the emotions, the anxiety, things that could attribute to people getting maybe a little sad, this may be there someplace, but I think this team stays so focused. And one of the things that I must acknowledge is that when you have a team that's so distributed in different locations, all of the things that Paul and both Susie has mentioned would never be possible without thousands, I would say, of people doing multiple things. So you have to be proud, right, when you look back and say, look at the team that's operating Spitzer, look at the team that's contributing to having all of this great science.
And the Spitzer team has so much to be proud of, that's for sure. And you've been with this mission since before it launched. And so after the last 18 years, what do you think that the Spitzer team as a whole will be most proud of?
Well, Marina, one thing I think that anyone would be proud of, but mostly when you say the team is, a lot of our team members, we've had these new families that's been created over the life of a mission of 16 years long. And now some of the members of the team are showing their kids some of the images that's coming down from Spitzer. But not just their kids, we're sharing the information with schools and others, right? And to be able to say, I'm a part of that new science that's coming down, I think anyone within the team would be just more than proud, because again, the team is what makes the science matter.
That's so true. And for generations to come, they'll be able to enjoy what Spitzer has accomplished. And Susie, why is it so important to observe in this particular part of the spectrum?
Well, in the infrared, again, it senses cool objects. And so we can see through dust. We're lifting the cosmic veil on the universe. And there's just a cornucopia of astrophysics objects out there that we can observe. There's, again, nebula, supernova, dying stars, stellar nurseries. The list goes on, and it's really remarkable. And in particular, we also can discover things in our own solar system. And one of my favorite discoveries for Spitzer was a new ring around Saturn. And this was only made possible by observing it in infrared light. The ring is 300 Saturns in diameter, so it's gigantic. But the particles are tiny and tenuous and diffuse, and it was only the cool radiation given off by those particles in the ring that Spitzer was able to detect it, and no other observatory had detected it before. So it's a fun discovery. It's right in our backyard, relatively in our solar system, relatively speaking. Correct. So it's one of my favorites.
That's amazing. And that's right, in our own solar system and far beyond. And that's what's great about Spitzer, is it's discovered so much, and beyond into our universe we'll continue to explore into the future. And Joseph, much of the Spitzer's team is original to the project, which is pretty amazing. Do you think it's because Spitzer was able to accomplish so much in its over 16 years?
Well, when you say original, one thing I would like to really point out is that the teams that we've had, the people who have worked on Spitzer, they have a sense of ownership to the processes and their designs and things that they have developed. During any anomaly or issues that we've had, the teams have always had the ability to reach back When I say reach back, meaning some of the heritage knowledge people have come forward to help us resolve issues. That's a really great thing to have on any mission today or any day, right? So looking back over all of those many years, I think having all of that heritage knowledge, having the folks to be there available is one of the great attributes that has contributed to the success of the mission.
And it has been a success, for sure. And each telescope in the 4 great observatories operated in a different part of the electromagnetic spectrum. What is the infrared portion of the spectrum that Spitzer worked in, and why does it work so well? How do you make sense of something you can't see? This is the electromagnetic spectrum, where light travels in waves. Without it, the world you know could not exist. The human eye can only see this very small part of the spectrum, called visible light. But a whole new universe is revealed by looking through the infrared. Infrared light can't be seen, but it can be felt in the form of heat. Every object, whether hot or cold, gives off heat. Special thermal cameras use colors to show us if something is warm or cold. Some objects are hot enough to show visible light, and things that are too cold to be seen by the naked eye can let off an infrared, such as your body or this cup of coffee. IR light can be used in very practical ways. Longer IR waves can cook your dinner. Shorter IR waves that are used in your TV's remote control, and firemen use IR cameras to see through smoke to find people trapped in a fire. So how does this apply to a telescope? On top of showing us colder objects, infrared wavelengths can see through large amounts of gas and dust, lifting the veil to what lies on the other side. Spitzer sees objects like exoplanets or the Milky Way by looking at their infrared glow from the heat they give off. This gives us the ability to see what is beyond, and that's IR in a minute. Thank you so much, Joseph and Suzanne. As a reminder, we are inviting everyone to ask questions of our panelists. If you are a member of the media on our phone lines, press *1 to be put into the queue. And if you are on social media, make sure you use the hashtag #AskNASA. So now that we understand Spitzer's role in the 4 great observatories and its ability to gaze into the infrared universe, here to tell us about some of the amazing discoveries in science that came from this telescope are Michael Werner, the Spitzer Space Telescope project scientist, and Farissa Morales, a Spitzer scientist. Welcome.
Thank you, Marina.
My pleasure, Marina.
What a wonderful day we are celebrating here today. An incredible revelation about Spitzer, Mike, are the many observations and discoveries that it made that it wasn't originally planned to do, like exoplanets, for example. Now, Spitzer studied hundreds of exoplanets and was one of the first to study the atmosphere around these exoplanets, and perhaps its most famous exoplanet subject was the Trappist One System. Can you tell me a little bit about this system?
Sure. I'd like to do a little demonstration
Please
here.
do.
This grapefruit is the star. This ping pong ball is a planet. And we know from so here's the planet going around the star. We know from the Kepler Space Telescope that most stars in our galaxy have planets around them. And because of that, there are many cases in which the planet is orbiting edge on as we see it. So we can see the planet move in front of the star. That's the case of the Trappist system. When the planet moves in front of the star, you see a little less light from the star than you did, and now it comes back out, you see more light from the star. The depth of that drop tells you about the size of the planet. And if this is an orbit where it goes around, say, every 3 days, the length of the orbit tells you how far from the star the planet actually is. And you can get lots of other information by studying these so-called transiting planets. It's quite remarkable how much information you can get about planets which you never really see distinctly apart from the star. In the case of the Trappist system, there's a beautiful artist's conception there. We monitored it for 20 days with Spitzer, which is possible in our orbit because of the freedom and distance from the Earth and the Moon, and saw so many patterns, interwoven patterns of transits, that we had the team that was working on it sort of sorted all that out and found that there are actually 7 planets orbiting that star, quite snuggled up close to it. It's a faint red star. And of those 7 planets, they're all about the size of the Earth. We expected about 3 of them are in the habitable zone, which is where water would be liquid on their surfaces, which is important if we feel it's important if they're going to harbor life, or if they do harbor life. So this system has been well studied by Spitzer. It's the best characterized solar system outside of our own, and it's sitting there awaiting the James Webb Space Telescope, which Paul will be talking about later, which will provide additional information about this exciting and surprising system of exoplanets.
It's amazing because in the end, the science will just continue to live on.
Absolutely.
Which is amazing. Now, my personal favorite is the 360-degree view of the Milky Way. It's so fascinating. How was Spitzer able to map out that Milky Way so extensively?
Well, the Milky Way survey, which is called GLIMPSE, is an example of a legacy science program that we initiated early on to enable teams to do really big projects. Now, to do this big image, Spitzer had to be, first of all, very sensitive. Because it's cold and in space, it's free of the contamination of foreground infrared radiation. It views against the cold background of space as opposed to the warm infrared background of our atmosphere, say. So Spitzer is very sensitive. Each image that went into that composite took only a few seconds. It has a big field of view. It sees a big piece of sky at one time with what's called an array. Kind of think of the camera in your cell phone, lots of pixels, that's Spitzer's camera. Also, Spitzer is very maneuverable. It's a compact and tightly constructed spacecraft, so it can hop from one image to the other very quickly. And the other thing that enabled this was our orbit. Because of the fact that we're far from the Earth, we don't have to worry about where the Earth is as we're planning our observations. We could set aside huge swaths of time to allow the team to bite off big chunks of the Milky Way, one after the other. As a result, we have a database in our archive with millions of sources in it: young stars, old stars, evolved stars, interstellar dust, interstellar gas, an archive which has already given birth to hundreds of scientific papers and which will continue to be used by scientists far into the future.
And what was great about Spitzer is you could use it for lengthy periods of time.
Exactly.
When you were looking at one object. I believe you said 40 days was spent on the Trappist system?
20 days of intense round-the-clock observation, and then 20 additional days object by object to determine their characteristics more completely.
And for the Milky Way, it was less, but still.
Oh, no, it was more.
It was more.
Yeah, it was thousands of hours when all was said and done.
Oh, that's amazing.
It's a remarkable data
Well, it was
set.
worth it to be able to get that picture.
Absolutely.
That's for sure. And Farissa, welcome.
Yeah.
Now, Spitzer is almost like the little engine that could. We always talk about this. And why do you believe that Spitzer was so revolutionary? Joseph talked about how the mission endured with a strong team, and Mike talked about that science that it returned. That's just so amazing. And why do you think it lasted so long?
You know, Spitzer Space Telescope really is, or has been revolutionary because it's the effort of hundreds of people coming together. Just to mention a few, I mean, from private industry like Lockheed Martin and Boeing and Ball Aerospace, universities building instruments to build the telescope, Caltech with the Spitzer Science Center supporting the science, and JPL, right, supporting the project, the operations, the Deep Space Network to communicate with it. So it's hundreds of people, lots of teams coming together to make it work for thousands of astronomers to use. And you can just imagine, after over 16 years of observations, a tremendous wealth, right? The archive that we have, which is a repository of data, of infrared data that is waiting to be mined.
And I know you guys can't wait to get to that, that's for sure. Well, Spitzer is very famous for its beautiful imagery. What people don't know is the picture we see is not something Spitzer just takes a picture of. It's a lengthy process from capture to awe. The Spitzer Space Telescope has blown us away with incredible imagery over the last 16 years. However, getting these images is much more difficult than you may think. Spacecraft images are not photographs, but pictorial presentations of data. Satellite systems measure light at different bands of the electromagnetic spectrum. In Spitzer's case, it's the infrared. This is raw data processed from Spitzer. To analyze this flood of numbers, scientists rely on computers, not only to do calculations, but also to change data into images, similar to the process our digital cameras use to get that perfect picture. Even with the computer, scientists go through a painstaking process to make sure the images are technically correct, so the raw data gets turned into this. Spitzer's infrared images are not true color images. Since we can't see infrared wavelengths with our eyes, scientists pick representative colors to show the infrared light detected by the telescope. Computer-aided data collection and processing is essential, but the scientists truly bring the data into a visual piece of art that we can enjoy and understand. And that is the art of Spitzer in a minute. And what incredible imagery we will be able to enjoy for generations to come. Now, Spitzer's images are just breathtaking. What do you think Spitzer unveiled, Farissa?
Spitzer Space Telescope has unveiled the infrared universe. I mean, it has allowed us to see what our human eyes could not see. And as you saw from the video, these huge molecular clouds in our galaxy, which are stellar nurseries, become transparent when you're observing in infrared radiation. And it allows us to see these baby stars forming in hundreds of light years across. And the process of forming a star, some of the debris is left over to form and coagulate into little planetary systems. Spitzer has been a pathfinder in allowing us to find out which ones are forming now for future exploration.
Stellar nurseries. Amazing that it can peer into that. And as a Spitzer scientist, how do you analyze all of that data?
Yeah, there's two things you can do with light, any flavor of light, in this case infrared light. You can do photometry, which is basically counting photons on how much light falls on a pixel, which is basically what our phones have. Or you can do another technique called spectroscopy, and with spectroscopy the light gets broken down into its rainbow components. And you can analyze how much light you're seeing per wavelength, how much energy. And that is very interesting, an interesting technique and an amazing technique that humans have to then allow us to obtain information from the dust, for example, that emitted that radiation. And when you analyze through spectroscopy the composition, for example, you can obtain the chemical composition of the dust orbiting around another star. And you can also get information about the structure of, for example, other planetary systems that are forming. So it's amazing how data can be studied and how much information it brings us.
That's amazing. From an engineering marvel of a telescope to its beautiful science return, that's for sure. And there will be much to speak about when it comes to Spitzer for generations to come, I feel. But Mike, what do you personally think its legacy will be?
Well, to begin with, several of us have already mentioned the archive of data, which is already being mined by astronomers and will continue to be mined for decades. An important science area that's well represented in that archive is the study of the very distant universe. We've talked about exoplanets, which are nearby, but Spitzer, particularly working with Hubble, has seen galaxies as they were when the universe was only a few percent of its current age. And they, like the exoplanets, will be well studied by the James Webb Space Telescope. But there's a human dimension to the legacy as well. And again, Joseph and Farissa both hinted at this, which is the importance of the teamwork as an example of what people can accomplish when they're well-led, well-supported, and empowered. The work of the Spitzer team in producing this amazing observatory and using it so effectively is absolutely astounding. And I think it stands as a sterling example of what people are capable of doing. And I think that's important in these troubled times, to realize that there's a genius and an ability and a strength in the human spirit which is capable of doing amazing things. So that's another part of the legacy.
Well, you should all be so proud because it is just absolutely amazing. Thank you so much. Now, Spitzer was such a powerhouse in NASA's astrophysics portfolio and will continue to bring a wealth of information as we move ahead. Here to talk about why Spitzer is ending and its legacy yet to come through future missions is Paul Hertz. So, Paul, tell me a little bit about why we are ending Spitzer's mission and the science that will live on.
Well, Marina, at NASA, we review all of our missions for their science productivity as they go along through their mission. In 2016, we looked ahead and saw the upcoming launch of the James Webb Space Telescope, NASA's next great observatory, which is also an infrared observatory. And the decision was made that the Spitzer mission should end as the James Webb mission was beginning. At the time, we extended the Spitzer mission all the way through the launch of James Webb in 2018. When the James Webb launch was delayed until 2021, we extended Spitzer until now in 2020. But the time has come for the Spitzer mission to end as we move on to the launch of James Webb next year. Operation of Spitzer is becoming more difficult as it gets further away from the Earth, as the angle between the Earth, the Sun, and the telescope changes, makes it more difficult to simultaneously keep the solar panels pointed at the Sun, to keep the communications antenna pointed at the Earth, to keep the telescope pointed at the stars and planets we want to look at, and to keep the Sun off of the telescope so that it stays very cold and is able to continue its infrared. We can continue to operate it today, but in the very near future, it will become very difficult to continue operating the Spitzer Space Telescope.
Thank you so much, Paul. Now we're going to open up the panel to our media and social media questions. And our first question is on the phone from Stephen Clark with Spaceflight Now. Welcome, Stephen.
Hi, thank you all for doing this and for taking my question. I just wanted to get an update maybe from Mr. Hunt about the process to shut down the telescope. Have science observations already ended, or are you still getting down some final images over this next week? And can you talk about the process to shut down the telescope? What commands will you be sending to turn it off and to save or passivate it? And maybe for Paul Hertz, do you have the total life cycle cost for the Spitzer Space Telescope from development through end of mission? Thank you.
Okay, sure. So I'll go first, Paul. And yes, so over the course of the next week, we still have a set of science activities that's scheduled to be ran on the telescope. We'll complete most of our science activities on the 28th and complete our final science playback on the 29th. Then continuing forward, what happens for the end of mission? Passivation or safe mode in place. So for the Spitzer spacecraft, because of what Paul had mentioned earlier about extending the operations to couple with JWST, JWST was delayed. Spitzer still had some extended operations and science. We've reached a point that what we're going to do is utilize the engineering time, or what we did was utilize that engineering time to really focus on returning more science. As far as passivation, there's really nothing on Spitzer that you would need to passivate. We use nitrogen to keep it stable, which is a very inert gas. Based on the orbit, which Susie mentioned, our orbit, we're receding away from Earth. We're about 160 million miles away. We'll continue out on this trajectory. So really there's nothing out there for Spitzer to crash into other than some field of debris. So there's nothing there. So what we're going to do is on the 30th, we're going to put Spitzer in a hibernation mode, per se. We're going to command it from the ground to put it in safe mode. In safe mode, it goes into a sun coning attitude, and it will just stay in that attitude forever. And I think you had a second part of your question about costs to Paul.
Yes, Paul, would you be able to answer? Yes, would Paul be able to answer Stephen's second question?
So that's a great question, and we should have been ready for that one, but quite frankly, we haven't. I don't have that number off the top of my head.
Okay, great. Okay, next question comes from Kimberly Cartier from EOS. Hello, Kimberly.
Hi, thanks so much for taking my question and for putting together this event. Now, given that the James Webb Space Telescope is obviously not launched yet, and it's going to essentially take over for Spitzer in terms of infrared coverage, is there any concerns about the gap in coverage at these wavelengths?
Paul, would you be able to answer that question for Kimberly?
Sure, I'll be glad to. There's no concern about the gap because the universe, we're observing it now with Spitzer. Starting next year when the James Webb Space Telescope launches, we'll be observing it with James Webb. The James Webb mirror is 50 times larger than the Spitzer mirror, so we'll be able to observe even deeper into the universe. In fact, James Webb is designed to detect the first light after the Big Bang, the first stars and the first galaxies. And even beyond that, we're started building the Wide Field Infrared Survey Telescope, WFIRST, which will be the great observatory to follow Webb. WFIRST has the sensitivity of Hubble, but 100 times the field of view. So with every WFIRST image, we'll be doing 100 Hubble deep fields. So we're well positioned to continue studying the universe in the infrared, and the gap of a year or so really is not a concern.
Thank you so much, Paul. And now we head over to social media. Remember, if you want to ask our panelists a question, head over to social media and hashtag AskNASA. This is from @Dan Biko, and Dan would like to know, this is sad news. Is there a replacement in the works? And I think that, Paul, you just mentioned we've got James Webb and WFIRST, if you want to go ahead and talk a little bit more about that.
Right. Well, while neither Webb nor WFIRST will exactly replace Spitzer, they both are built on the legacy of Spitzer. First of all, the science that Spitzer did has revealed a lot of mysteries of the universe that we want to follow up with Webb and WFIRST. In addition, something we didn't talk about is that Spitzer demonstrated passive cooling of a telescope. The Spitzer telescope is kept cold by just radiating out into space, and it's only a few tens of degrees above absolute zero. It doesn't require a complex cooling system to stay cold, and that's exactly how we're going to keep the James Webb Space Telescope mirror cold. Even though it's 50 times bigger than the Spitzer Space Telescope, we'll cool it down to below 50 degrees above absolute zero by passively radiating out into space, a technique that was developed and demonstrated by the Spitzer Space Telescope.
Thank you so much, Paul. Our next question from social media is from Iris. Iris wants to know, what is the Spitzer team going to be doing after the shutdown?
I'll take that question, Iris. So, good question. What will the team be doing? So, actually, we're closing out the mission, and shutting down the observatory is just one phase of that. During the closeout, we decommission the flight and the ground assets. So once the spacecraft is declared decommissioned, we'll start the closeout process for archiving all of the documentation and all of our non-science data, which is the engineering data that we've collected off the observatory for the many years of operations. So that will continue throughout the year.
Thank you so much, Joseph. Now we have Megan Bartel from space.com on the lines. Thank you for joining us, Megan.
Thanks for taking my call. Can you hear me?
Yes, I can.
Great. This is a question for Mike. If you could just, you've talked about the science a lot, but if you could summarize sort of what your own personal favorite discovery from the mission is, that would be great.
Well, from the very big picture, clearly the results on exoplanets and the results on the distant universe are the two major areas of Spitzer's contributions, as we discussed earlier. But I have a soft spot in my heart for several smaller discoveries, and just to mention one of them, my colleague Mike Jura from UCLA discovered that you can determine the composition of exoplanetary systems by studying the atmospheres of white dwarfs. Sounds very surprising, but a white dwarf which is an evolved star, if it had a planetary system while it was on the main sequence, part of that planetary system, comets or asteroids, may approach the white dwarf, get torn apart by its very strong gravity. That material will fall onto the atmosphere of the white dwarf and can be observed because the atmosphere is polluted by that material. It's a very solid but somewhat roundabout way of studying the composition of extrasolar planetary systems, which really can't be done any other way. So that's just one of several little gems that I followed with great delight over the years.
Wonderful, wonderful. We also have a follow-up question right now from Kimberly Cartier from EOS. Welcome back, Kimberly.
Hi, thanks so much for the opportunity for a second question. Sort of following on to that, are there other observations from inside the solar system or of solar system objects that are particularly exciting for you or anyone else?
Yeah, I think the most exciting, apart from Saturn's rings that Susie mentioned, the most exciting solar system result came early in the mission, when the Deep Impact spacecraft collided with the nucleus of a comet and put out a great spray of gas and dust. Spitzer and many other telescopes observed that in detail because it was a first look at the primordial material buried beneath the crusty outer surface of a comet. And very interestingly, we found that the composition of that material, which contained a lot of silicate minerals and so forth, was very, very similar to the composition of material which we see around exoplanetary systems, in exoplanetary systems. And that's just one of many ways in which Spitzer established important links between our own solar system, which we study well from inside, and these external systems where we can see them from the outside and sort of get a bigger picture. But there are lots of commonalities which have improved our understanding of both the solar system and exoplanetary systems. The similarity in composition is just one of those.
Thank you so much, Mike. We also have a follow-up question from Stephen Clark from Spaceflight Now. Welcome back, Stephen.
Hi, thank you for taking another question from me. To follow up on my earlier question to Joseph Hunt, so the spacecraft is going to go into a safe mode. Is turning the receiver and radio transmitter off part of that process, or do those remain on, and is there any possibility to reestablish contact with the spacecraft at some point in the distant future? Thank you.
Yes, thank you. So one of the things Susie mentioned in her discussion was the orbit geometry and how the spacecraft recedes away. As we're getting further away, the radio signal continues to weaken, so the possibility of contacting it becomes more complex and more difficult. Again, one of the things that I included earlier in talking about the closeout, so when you're decommissioning the spacecraft, you also decommission the ground system. Spitzer used a very customized ground system to create the science sequences and the products that you need to collect the science. Once that system is dissolved, it makes it very difficult or impossible to resurrect. So the likelihood of recommanding or resurrecting science operation with Spitzer would not be there.
Thank you, Joseph. And we have a question on social media from Manish. What is the future of exoplanet discovery once NASA Spitzer stops collecting data? Paul, can you take that one?
Sure, I'll be glad to, Marina. But before I do, let me say that we have found the total cost of the Spitzer mission from a previous question, and the total cost is $1.36 billion spent over the last 20 plus years. That includes building and operating and launching the observatory. So 2 years ago, In 2018, NASA launched its next exoplanet mission, the Transiting Exoplanet Survey Satellite called TESS. TESS is surveying the entire sky looking for transiting exoplanets around the nearest and brightest stars. It's already found over 1,000 candidate exoplanets in just its first year and a half of operations. We've approved TESS for another 3 years of operations so far. And so the future of exoplanet studies is very bright. With the TESS telescope discovering new exoplanets. James Webb Space Telescope, which you've already talked about, will be launching next year, and one of its key science areas will be characterizing individual exoplanets, the most interesting ones, using its suite of 4 very powerful instruments on board. In addition, the Hubble Space Telescope continues to study exoplanets.
Thank you so much, Paul. And I think one of the most amazing things, at least for the public, to fall in love with Spitzer has been from its many incredible images. And I know each of you have your favorites, so if we could just go down the line and you could tell me what your favorite Spitzer image is, I would appreciate it.
Yes, Marina. My favorite image is of a region called NGC 1333, where stars are forming. It's very colorful. It shows a progression between the very youngest stars and slightly older ones. And this is a geometrical progression in space. And you can imagine that there's a wave of star formation propagating along that trajectory. And each generation of stars triggers the star formation, the next generation, by the pressure that it puts on the surrounding molecular gas and dust. So my vote is for NGC 1333.
Well, I have many favorites, but I'm going to highlight one that was very impressive to me. It's called Mountains of Creation, and it's an amazing, very impressive, hundreds of light years across molecular cloud that shows the erosion of this cloud as it forms baby stars. It's very impressive to me.
It's a beautiful one. Yeah. Joseph?
Hi, Marina. So that's a really difficult question because, you know,
so many to
when
choose
you
from.
go, absolutely. I remember for our launch anniversary, we were putting together images, and that same question was asked, and you spent minutes just strolling through. But Mike explained the science of it, and I think looking at the graphic or the artist concept of it for the Trappist One system would probably be my most favorite.
Wonderful. Susie?
Well, besides Saturn and Saturn's rings, I really like M81, which is just a classic spiral galaxy. And I think that kind of epitomizes what Spitzer can do in the infrared and how you can just dig into that data and see the star forming regions, see the regions where the stars are also dying by sort of just changing the wavelengths that you're looking at and stretching the colors a little bit. It's just the classic Spitzer image in my mind.
And the galaxy pictures are just so beautiful. I love the Crab Nebula. And there's just so many beautiful ones to go online and research and look up. And I hope that everyone's love for Spitzer will get reignited and they'll be able to go out and do a lot of research on their own. Thank you so much, all of you, for being here, and Paul back in headquarters. And we are going to end our show now. Spitzer is not that far away from us in relation to the cosmos as a whole, but it has managed to unlock secrets within our own solar system, plus galaxies and nebulas that are millions of light years away. Spitzer will continue to impact us on our future quest for knowledge. For more information on the Spitzer Space Telescope, please go to www.nasa.gov/Spitzer. Thank you so much for joining us today. We will leave you with a look at the numerous breathtaking images from the Spitzer Space Telescope.
rolling on the moon one day. In a merry, merry month of December. Now, May, when much to my surprise,